Hi, everybody. We're going to jump into chapter 6, as hopefully you can see there on the screen. As I go through this, I want to apologize. I'm not sure exactly how this is going to turn out, but if you hear Silas off to the side with one of his chew toys, we all know that he can chew very loudly for a little puppy dog. Now, as we go through the next unit here, obviously, as you can see, we're starting in the middle of this chapter. We are not going to go back and do any of those other things. Don't have to worry about that. But looking at conic sections is a worthy topic here for, since you didn't cover this in Algebra 2, we're going to take some time here to look at this in pre-calculus and hopefully making the connections here to what we just did in that first unit. You are going to need the completing the square method. So there are four different curves that are classified as conic sections. In this section here, we're going to, hopefully you are familiar with, you know some things about parabolas, but maybe I'm not so sure about the geometric description of how to create a parabola. We're going to look at several different properties here, hopefully adding to what you already know about parabolas, and then also setting us up for success looking at the other ones. Okay, so oh my goodness, that's a mess. This is somewhat intimidating. Don't let yourself be discouraged. This is a second degree equation with two variables. This is as complicated as it possibly can get. We have ax squared plus b times xy plus cy squared plus dx to the first plus e times y to the first plus f, which would be a constant, set equal to 0. Now again, it's second degree, so it's a quadratic equation. If a, b, and c are not all 0, then we're going to have something that's called a conic section. Now, again, you're already familiar with the parabola. Let's add to our list here. They throw the terms at you. We will study each of these in depth as we going along. Um, Circle, ellipse, and hyperbola in addition to the parabola. Again, get the pronunciation right. It's not a parabola, so the other one is not a hyperbola. So this is general form for all quadratics, and I'm going to come back to this at a later lesson and talk about how we should be able to identify which type of conic section it is by looking at those values for just A, B, and C. Why do we call them conic sections? So if we take a line, of course, infinitely long, and pick a point, doesn't matter, let's call it V for vertex, yep, and take another point and rotate that around 360 degrees. We're not only going to get one cone, we're actually going to get two of them that are connected at that vertex point, okay? And those are the upper nap and the lower one. Conic section means we're going to slice through this. We're going to take a section of this double napped cone. All right, parabola, the first one that you see there on the left, with which you hopefully are familiar. If we take a section of this double napped cone so that it intersects one of the bases, if we cut it so that it is a plane that's parallel to that line of generation that we used, This curve is the parabola. If looking at the middle figure there, if we cut parallel to the base, well, you know that the base of a cone is a circle. And if we cut a section through it here parallel to the base, we're going to get another circle. The closer we are to the base, the bigger the circle. The closer we are to that vertex point, the smaller they get until it's just a single point. If we cut through the cone so that it's neither parallel to the base nor intersecting the base, we get a circle that's kind of stretched out. That's an ellipse. And if we cut through both parts of it, we don't just get a parabola, we get something that's called a hyperbola, the last one there on the far right, where there's actually two different parts to just that one curve. Okay. To me, they kind of cheated here. They used one picture to show you both a circle and an ellipse in the middle. But don't get it confused there. The hyperbola is a single equation, one single function here that has two parts to it. Then there's some crazy stuff that could happen. If we cut a section here, so the line that generated the cones is in the plane, we just get that generation line. We could cut through it at just the vertex parallel to the bases where we get just a point. We could pick the perfect angle there so that instead of some kind of a curve, which really might be interesting, we're just going to get two intersecting lines, which, kind of boring. So these are called the degenerate cases. They are possible, but we're going to try and avoid these outcomes here because, again, they're just not interesting. All right, so a different way of describing a parabola, a different way of defining it here is from a geometric standpoint. We can say a parabola is the set of all points in a plane, so again, just a two-dimensional figure, equidistant from a particular line and a particular point in the plane. Okay, so again, well, the distance from a point to another point, that's pretty easy. Of course, you remember, we measured the distance from a point to a line in a direction that's perpendicular to that line. Okay, so this particular point that we're talking about is the focus. Very, very important term. Make sure that you understand that. We're going to be coming back to it over and over. This particular line in our definition here is called the directrix. So again, we find all of these points that are the same distance to the focal point as they are to the line. And again, we're going to measure that so that it's perpendicular. So over here, this point has to be on the parabola because that distance and this distance are the same. So that's the same. These are the same. These are the same. And once we get enough of these points, it forms a parabola. And again, hopefully you're familiar with that shape already. Take a look at that general form up there. Again, you're probably somewhat familiar with this. If we have y equals x squared, well, that's the simplest equation of a parabola that we could possibly get, going through 0, 0 as the vertex. But now let's take a look at things here, maybe from slightly different from our definition of the geometric definition of the parabola. We're going to put this in the form of x squared equals 4 times p times the variable y. Now again, we also always have to have the x and y, so we get coordinates here. The interesting thing is for this value of p, that's going to be kind of like what we did with y equals mx plus b. Okay, it's going to be the y coordinate of the y, no, wait, hold on, it's not the y-intercept in this case, it's the y coordinate of the focus. The x coordinate is going to be 0. The focus is going to be on the y-axis. The vertex is going to be a huge thing here, halfway between the directrix and the focus. Again, the directrix is that line that helps us form the parabolic curve. Now again, we can have this if the value for P is positive, the focus is above the vertex point. Because they're equidistant, then the directrix is below the vertex point. If that value for P is negative, well then the focus is going to be below the vertex and the directrix above it. So again, if we're just going to try and keep it simple here to start with, if we put the vertex of the parabola at 0, 0 at the origin, we can have y equals x squared, 4y equals x squared, 16y equals x squared. If that value for p is positive, it's going to open up. If that value for p is negative, it's going to open down. The focus is going to be at the point 0, p. The directrix, again, here the directrix is a nice horizontal line. All horizontal lines have an equation of y equals some constant. The axis of symmetry is going to be the y-axis itself. The focal length, we're going to say, is, again, that value for p. The focal width, we'll get to that in a moment there, is going to be that absolute value of 4 times p. Now contrast that with something that will pass the vertical line test to something that won't, but has the same exact shape if we switch it around to y squared equals 4px. So if p is positive, this is a parabola that's going to open to the right. If p is negative, this parabola will open to the left. And the focus, now notice everything flips. We switch the x and y variables. The focus is now at the point P0 instead of 0P. The directrix is going to be a vertical line. The axis of symmetry is going to be the x-axis now, but the focal length and the focal width are going to be the same. So here are examples of, again, just general generic form. If it's y squared, again, obviously fails that vertical line test, but it's the same exact shape. So we're going to study these two. So if it's 4x equals y squared, 40x equals y squared. This is going to be, again, if p is positive, the one here on the left, it's going to open to the right, and the directrix is to the left. If p is a negative value, the focus is to the left. It opens to the left, and the directrix is going to be to the right. All right, so let's write an equation in standard form for the parabola, where the directrix is the line x equals 3, and the focus point is at -3, 0. Because that directrix is x equals 3, this parabola opens to the left. Okay, so it's x equals, so that's going to be, if we go back here, It either opens left or right. And if we're told in this case that it's x equals 3 is the directrix, -3, 0 is where the focus is, that means this one opens to the left. And again, our value for P there, the focal length is -3. We'll substitute -3 in place of P, multiply that by 4. That's it. There's our equation. Suppose we move the vertex. Now again, this I'm hoping should look somewhat familiar. Okay, not sure if it was Algebra 2 or Algebra 1. If we move the vertex away from 0, 0, and we put it anywhere with coordinates h, k, we're going to have the standard equation. We're still going to use that 4 times p to emphasize finding where the focus is, finding where the directrix is, finding that focal length and focal width. We're going to have to do some factoring, though. So again, if p is positive, it opens upward, negative, downward. If it's y squared and p is positive, it opens to the right. P is negative, it goes to the left. Find the standard form of the equation of a parabola where the vertex is at the point 1, 2, and the focus is at 1, -2. Ooh, have you already graphed this in your mind? All right, how about looking at one then? If the vertex is at the point 1, 2, there's my vertex, and the focus is at 1, -2, again, the way this is shaped, the focus is going to be inside the curve. Because the focus is below the vertex, this opens downward. If it opens downward, here's the equation that we're going to use. Here's what we need. Again, if it opens up or down, it's going to be the x that's squared. So how about we do a little bit of substitution here? We are told that the vertex is at the point 1, 2, so we could substitute those in place of h and k. Now again, if we're going from the point 1, 2 down to the point 1, -2, that's a distance of 4 spaces. Because we're going down, I'm writing over it here, that value for p should not only give us a distance, but also a direction, depending upon whether we write it as positive or negative. So in this case, again, going from 1, 2 to the point 1, -2, it's a distance of 4 spaces, but because we're going downward, our value for p here should be -4. Substitute, simplify, there's the equation. X minus 1 quantity squared, leave it in its factored form, is equal to 4 times -4, so that'll be -16 as the coefficient out front. Again, leave the set of parentheses, y minus 2. Again, parabolas are extremely useful. Once you start doing some searching for things, you may be surprised. Every single flashlight has a shiny surface that's the shape of a parabola. The headlights, both the high beams and the low beams on your car, have reflection reflective surfaces there that help focus the beam. It's parabolic. Satellite uplink, satellite dishes, I think. The fact that it will take a source of light, reflect that light, and focus it is one of the reasons that a parabola turns out to be such an amazingly useful shape. Okay, but hold on. Flashlights and headlights and all of these things here are three-dimensional. So we take this thing and we rotate it around the axis. Again, that axis of symmetry. We rotate it 360 degrees in three-dimensional space. It's a paraboloid. So the reflector of a television satellite dish is a paraboloid of revolution. For one of them here, we're going to say the diameter of this thing is 5 feet. It has a depth of 2 feet. The signal from the satellite is going to be collected and focused. Yeah, that's why we call it a focal point. It's going to be focused where? How far from the vertex should the receiving antenna be placed? Okay. So if you've got that picture in your mind, it's a parabola that opens upward. If we're, again, trying to figure out how far from the vertex we need to put that receiving antenna, let's make this easy on ourselves. Let's put the vertex at the origin of a coordinate system. So the focus F has to have coordinates 0, P. Again, vertex at 0, 0. We're using the much simpler version of the equation of a parabola. X squared is equal to 4 times py. So it's 5 feet across, 2 feet deep. Again, if we're saying this is 0, 0, this point up here is the point 0, 2. So we go 5 spaces to the right. Sorry, not 5 spaces. It's a 5 feet diameter. So that puts us at 2.52 on this side and negative 2.52 on that side to give us that total distance there of 5 feet. So we need to find the value of P in this case. We'll take that basic equation that we just had here, x squared is equal to 4py, and we're going to substitute the coordinates. Now, again, remember, this point right here is not on the parabola. We need these points left and right that are on the parabola with the vertex at 0, 0 to write this equation. So we substitute 2.5 for x and 2 for y into the equation. So x squared is equal to 4 times p times, well, y is 2. And it really doesn't matter if we substitute in 2.5 or negative 2.5 because we're going to square it. That'll give us 6.25 is equal to 8 times p. Divide both sides by 8. So the value there for p is 0.87125 feet. A fraction of a foot, let's convert that into inches by multiplying by 12. So the receiving antenna should be placed inside the dish along the axis, a distance of 9.375 inches from the vertex. And again, we have equations. Don't be intimidated by this. I don't know how to, you know how to substitute values into an equation and solve for a variable. You know how to do this. Okay, so again, take a look at what's on the Pearson website, and we'll talk about all of this, answer any questions that you may have when we get together next time.